Speaker is Professor Himansu Biswal uh, from NICER Bhubaneswar. Professor Biswal has a talk with a slightly different title than what is given in the abstract book. Hydrogen bonds with sulfur and selenium. A voyage through 4-atom dimer to 14 kilodalton protein.
Okay. I should thank Professor Arunan for giving me opportunity to contribute to the 100th issue of Journal of Indian Institute of Science. At the same time also he is giving me opportunity to present my work here. So I apologize for having the wrong abstract published in the journal. Actually I sent the corrected one, unfortunately it was not there. Anyway, so it doesn't matter. So what I'll do, I'll start from this one. This cartoon actually it's a impressive cartoon. So I'll start the smallest picture here. So I'll start with the smallest hydrogen bonding dimer where sulfur can participate for the hydrogen bonding. I'll go to the largest one till now what I studied or our group studied. This is called ferredoxin, which is 14 kilodalton protein. So at the end I will give you something different and I will finish my talk the way the tail ender finish in cricket. Okay, something different what we learned till now. Okay, so what we look on, so we work on hydrogen bond with its alkogens. So using different spectroscopy methods, gas phase laser spectroscopy, that is my basic training. So now I am started using NMR also, and all these spectroscopy are supported by the quantum chemistry calculations. So I have a good bunch of young students, PhD students and postdocs, so who contribute a lot to understand these hydrogen bonds. So we also looked at the applications of these hydrogen bonds in electrical and optical responses, the protein stability, and some green chemistry, and mostly in the catalysis in water, how water is influencing water, hydrogen bond with water influences the catalysis. Okay, so this is the motivation to look at the hydrogen bond in the hydrophobic core on the proteins, not hydrogen bond, non-covalent interactions in the hydrophobic core of the proteins. So here I will present actually out of many interactions, I will present the interactions with sulfur in the hydrophobic core of the proteins. So you might have already noticed that the disulfides may be sulfur also, or methionine sulfurs in the hydrophobic core of the proteins. Not only that, if you go back to the textbook, any biochemistry textbook, you will find this list of non-covalent interactions. Where is the okay. So if you look at the hydrogen bond, it's mostly takes oxygen as hydrogen bond acceptor, but there are possibilities of hydrogen bond with other acceptors. So let's start with the smallest hydrogen bonded dimer. So this is called sulfanyl radical, or it is called mercapto radical, hydrosulfide radical. So many names are there. So this one has importance actually. If you look at, so it can reduce actually this HS radical to form the S minus, and it actually activates the participates in cis trans isomerism in lipids. Actually this paper says that. So it was interest to look at such interactions. I tried doing the calculations. Can we have this SH interaction in radicals? So I started with a doublet SH and the whole dimer as singlet, and you can have always I found actually the optimum geometry is the disulfide bond. So when I took as triplet, there is a possibility of hydrogen bonding, and this hydrogen actually transferred to this one, but still this one the distance between H3 and H4 is within the van der Waals radii of sulfur and hydrogen, and the binding energy is too huge, it is 50 kilojoule per mole. This is just 1 week before I did the calculation, and it shows actually the typical analysis we do to confirm whether it is a non-covalent interaction or not, and it shows it has a bond critical point. There is a orbital overlap of a sulfur lone pair and a SH sigma star orbital. Then come to the next hydrogen bond dimer could be H2S dimer. So, that was published recently by Professor Arun and in microwave spectroscopy. Before that I was looking for the IR spectroscopy data, but I found actually there is a paper in 1999 where they have looked at the H2S dimer, and not only that they also looked at this one, the H2S and SH dimer. Okay. And in both the cases the SH vibrational frequency was shifted 40 and 60 centimeter inverse, or it shifted compared to the monomer. So, here our effort actually to probe the sulfur hydrogen bond. So, this was when I started my PhD, this was the setup actually we used to probe the sulfur hydrogen bonding in gas phase spectroscopy. I will not go to the detail as Professor Alok Das has already explained it. So, I will go to the result quickly. So, these are the compounds actually we used just to probe those hydrogen bonds in biomolecules. So, we took tyrosine, cutting off all these other backbone part, so that other hydrogen bonds or other interaction will not have in our dimers. For tryptophan we took the indole, and for sulfur acceptor we took a dimethyl sulfide as a model compound of methionine, and there are many publications for those work. So, what we observed, we started with H2O, we did a very systematic study. We started with H2O and the comparative one with the H2S. So, H2O this OH shift, the red shift for H2O complex is more comparison to H2S complex. We did for the methanol, unfortunately methanethyl was not available, we could not do that one and compare. If you look at ethanol and ethanethyl, in the ethanethyl cases, the ethanol still forms stronger complex than the ethanethyl. Okay. So, then we move to the ethers versus thiethers. So, we started again with water. Now, we see symmetrically substitute this hydrogen with methyl groups. So, if you look at in dimethyl ether, the redmost peak is at 3417, where in dimethyl sulfide it is 3408. So, now the shift actually changes their position. So, in oxygen case it is less red shift than the sulfur one. So, and that also true for the diethyl ether, and the THF THT, the tetrahydrofuran and tetrahydrothiophene, they have almost THF is little more red shifted than the THT. So, then we moved on, looked at the NHS interaction. Similarly, we started with H2O and H2S. In H2O actually it forms the NHO interaction, NHO hydrogen bond complexes, but its H2S it forms the SH pi hydrogen bond complexes. So, there is no comparison actually NHO and NHS taking water and H2S respectively. So, what we did then, we looked at in dimethyl ether and dimethyl sulfide, we see a more red shift in dimethyl sulfide than the dimethyl ether for the NHS hydrogen bond. Okay, so then we looked at actually, so when he said the sulfur can form very strong hydrogen bond, nobody was ready to accept at that time also. So, I came across during that time, during submitting my PhD thesis, I came across this paper, and this is a bioinformatics paper. They found lot of interaction with methionine sulfur. At the same time they wrote methionine is hydrophobic and the methionine sulfur is a poor hydrogen bond acceptor. Okay. So, that regard us to look at it in more detail. So, when I joined in postdoc in Michelmon's lab in France, so I told him, he had other projects in mind. So, I told him I want to do this study, and he actually is a very nice fellow. He allowed me to do to study this one using the laser ablation technique. So, what we did, we took a dipeptide, actually a capped dipeptide. This is a phenylalanine. So, we need a chromophore for our type of study. So, that is why the phenylalanine was chosen, keeping phenylalanine as a C terminal or N terminal. So, that is why you have FMP or MFP, okay, as well as we have taken the methionine. So, in this peptide you have methionine sulfur, you have many, and you have NH, and you have also the pi carbon or pi electron curve. So, if you look at, so there are many possibilities of a hydrogen bond in this small peptide. So, you can have a C5 hydrogen bond, what Professor Chakrabarty was telling on the first day. In a beta strand like structure, you can have a C7 and one C5, the C7 one is the gammaton, and or you can have a 2 gammatons or 1 betaton of C10. C10 means this number means the number of atoms in the cyclic structure. So, these are the backbone hydrogen bond pattern. If you look at the side chain, so you can have the sulfur can interact with this one with a C6 6 member ring, or with the NH with a 7 member ring, or with this terminal NH2 with a 10 member ring. Okay. So, you can have C6, C7, C10, and this backbone NH can have a NH pi interactions. So, now I have all the NH2 interaction, NHS interaction and NH pi interaction in one system. So, now it is easier to compare all of them. So, what we did, this is again gas phase laser spectroscopy. We actually found there are computationally there are hundreds of conformations, but experimentally we found 3 conformations, and this is the free NH2 where the NH is not at all bonded to any hydrogen any oxygen or sulfur or pi electrons. So, if you look at the brainmost peak here corresponds to the NHS hydrogen bond interaction. Okay. So, earlier people were thinking this NHS interaction could be as weak as NH pi interaction, but it is not the case. Okay. And whatever motif we observed, I then went back and looked at the PDB structure. These are the motif actually very exactly same type of motif C5, C7, gammaton, these are there in proteins. These are 2 examples given here. So, then what we did actually we looked at the Ramachandran plot also. These are the phi psi angles of these blacks are the experimentally observed one, these are also falling in the phi psi angle of the protein having the NHS hydrogen bonds. Okay. So, then the question comes, now I am comparing the amide NH and the carbonyl oxygen. So, I should compare, since my sulfur is a divalent sulfur. So, I should compare with a divalent oxygen. So, since methionine does not have oxygen counterpart, so what we thought of, we will compare this cysteine and serine. In cysteine you have a SH and serine you have a OH. So, that will be a direct comparison of NHS and NHO hydrogen bond. We did also similar type of experiment. What we observe here, this oxygen, this is NHO interaction and this is NHS interaction. This is also, this peak corresponds to NHO interaction, this is again NHS interaction. Okay. So, in cysteine now we have a direct comparison taking divalent oxygen, comparing the divalent oxygen with the divalent sulfur, and we observe that in that case also NHS hydrogen bond is stronger than the NHO hydrogen bond, or stronger or a similar magnitude. Okay. So, this is the computational analysis we found actually there is a interaction which is shown by the blue isocontour here, isosurface here, and this was published in Mississippi. Okay. So, this is the summary of this one. So, what happened actually is then the question arises, one of the referees said, So, in NHO, so the oxygen has a smaller van der Waals radius and the CO bond length is smaller than the CS bond length. So, you have more flexibility, so that the sulfur is reaching at the NH sulfur is getting closer to the NH than the oxygen. Okay. So, that was the argument for having NHS hydrogen bond stronger than the NHO. Then what we did, I thought of, let us remove all the relaxation. Okay. Take the simple models, this N-phenyl acetamide, this is cis-amide and trans-amide, just to mimic the nucleobases and the amides in the peptides. I took this one and then I took the other part. This can form the NHS hydrogen bond, this can form NHCO hydrogen bond, this can again divalent with divalent oxygen, and this one will be NH pi hydrogen bond. So, and I have removed all the geometrical constant here. Okay. So, I should thank my PI Professor Sanjay Vatekankar. So, he helped me doing the experiment. This time I came back to join Niger and I did the experiment there in summer. And what we observed, I have a free NH here, okay, for N-phenyl acetamide. This is the NHS hydrogen bond which is observed around 3376, NHCO which is about 3399, very close to this one, and 33773. If you look at, so whether it is sp2 hybridized oxygen or a divalent oxygen, so the NHS bond strength is very, in some cases it is stronger or very similar to that of the NHO hydrogen bonding, but it is far away from the NH pi hydrogen bond. Okay, it is far stronger than the NH pi hydrogen bond. That is what we proved here in this one. Anyway, so these are nothing, just the computation to support the experimental data. Okay, then we came back to the selenium to look at the hydrogen bonds with the selenium. So, when I looked at this is a paper actually, it is given people do here substitute selenium in place of oxygen because selenium is NMR active. Selenium is a heavier atom, so the diffraction will be easier, and it is NMR active and they use it in protein NMR also. So, when I looked at the PDB structures, I found a handful of this NHS selenium interactions, and this is just the statistical plot. This is within the van der Waals radii, the NHS distances, and you have about 2000 interactions in NHAC interactions in the proteins. And we did these calculations to see whether those are hydrogen bonded or not. Okay, and a similar way we did the experiment again at TIFR. So, this is NHAC which is observed at 3381 and compared with the dimethyl sulfide which is observed at 376. It is little blue shifted than the sulfur hydrogen bond, and similar the case for the pyridone also. So, this also suggests the selenium can form hydrogen bonds, and it is also though little weaker than the sulfur, but it is not as weak as the pi hydrogen bonding. Then what we did actually, I have many experimental frequencies. I did the DFT calculation so that I can have a scaling factor. So, I was interested to look at whether tellurium can form hydrogen bond. So, we didn't have the dimethyl telluride, so otherwise I would have done the experiment. I thought that will be good data for me to extrapolate to the tellurium, and we observe actually the tellurium also in terms of vibrational frequencies, tellurium also forms a hydrogen bond. Why is it so? Now, what I did, I plotted this might be coincidence, I cannot generalize till now, so I need more data to generalize this plot. So, if you look at this frequencies, NH frequencies, and this is the NVO calculation, donor orbital donor acceptor perturbation energies, the orbital overlap energy. So, if you look at it, it's actually we need to consider the charge Q stands for the charge of the sulfur, oxygen, selenium or tellurium, and alpha is the polarizability. Okay. So, I have calculated the charge of this one the whole in presence of 2 methyl group, and it actually correlates with the geometric mean of the this quantity, the charge and the square root of the polarizability. You have a very nice correlation, and this is actually the okay. So, then we looked at some selenium containing drug. Actually, when I submitted the paper, again the referee asked to show at least one application whether the selenium drugs can form the hydrogen bond in proteins or not. We found actually some there is a drug called analogous converting enzymes, and it forms actually those hydrogen bonds. Okay, so then now I finished the gas phase part. I will go to the solution. I have one example to show it. So, there are many reports regarding the thiamides. Even if this review, it has listed actually the free energies, hydrogen bond free energies for almost all the complexes, all hydrogen bond complexes except sulfur and selenium. Okay. And they have cited our paper taking our computational binding energy and telling this here binding energy could be that much of binding energy could be for the NHS hydrogen bond. So, what I thought, I will do some experiment to find out actually such interactions are there. If you look at nucleobase and protein complexes, such interactions are there actually with thiamide and this NH. Okay. So, then I looked at many such complexes, and I found actually in some of the cases they say the thiamide forms weaker hydrogen bond, some of the cases it says they say it forms stronger hydrogen bond than the amide carbonyls, actually thiocarbonyls and carbonyls. Okay, so we find okay, here I should, we find that in most cases effects of thermostability can be understood in terms of positioning the local environment of thiamide. This is a very nice paper, and they suggest it depends on the local environment, the constant you put on the thiamides, and thiamide can be a good hydrogen bond acceptor. Okay, so then I did a lot of calculation taking amide and thiamide counterparts, and we did many calculations, did the solvency corrections. So, anyway, the single point energy was calculated at CCDT level. Then the solvation correction I did with B97D, and we found actually there are plenty of coming back the questions. You can have hydrogen bond energy close to 60 kilojoule per mole. If you take, there are 2 hydrogen bonds, and if you take half of that, it is 30 kilojoule per mole, which is 8 kilocal, close to the 80 kilocal per mole. Okay. So, the hydrogen bond NHS hydrogen bond can be close to 10 kilocal per mole. Okay, so it is not computational. I will show you the experimental data. So, this is what I did the NMR titration, and this is the equilibrium you can choose. If I have a monomer at low concentration, I can have a dimer at a higher concentration, and this is the equilibrium you can choose. You can take the chemical shift as your observable, and you can have this this is the equilibrium constant for this process, and fitting the data you can have the free energies. Okay. Once I know the equilibrium constant and temperature, I can go back and calculate the free energies, and the free energies are very close. It is a minus 16.7 kilojoule per mole for pyridone dimers, and for about 15 kilojoule per mole for the thiopyridone dimers. Okay. So, we did also the Doshi experiment to confirm that this whatever at a higher concentration we are only observing the dimers, not the multimers. That is why we did the diffusion measurements. I did also the MD simulation just to confirm whatever experimentally the diffusion coefficient we are observing, experimentally observing, and the of similar magnitude also we are getting in the MD simulation. So, we also perform the deuterium exchange just to at a very high concentration. If you have a hydrogen bond complex, and if they have 5 minutes, I will finish, I have only 2 slides. If they have very strongly hydrogen bonded, the exchange rate should be same, okay, and that is what we observe for both pyridone and thiopyridone. Okay, so this is again the 2 weeks back our solid state NMR was installed. So, I was testing my molecule and I observed very nice thing. So, when we talk about this hydrogen bond, always we talk about the acceptor atom and donor atom. We never go back to look at what happens to the adjacent atom. So, I just monitor the carbon here, the 2. Okay. So, if you monitor this one, so for pyridone dimers, this is from low concentration to high concentration, it is downfield shifted, the C13 spectra. So, if you look at, okay, it is downfield shifted. If you look at thiopyridone, it is upfield shifted. Till now, I do not have any explanation. I am looking at the crystal structures in detail. Maybe some other time I can explain it. Okay, so this is the last part. So, this is the following our work. There is a paper here published in JACS. They suggest the ferredoxin activities because of the NHS gamma hydrogen bonds play important roles in modulating the mechanical and kinetic properties of iron thyroid proteins. So, this one this is the algorithm we designed to look at the protein database, and two of my MSc students, they are so good. Within 2 hours we can search the 10,000 of proteins. Okay. So, it is written in Python. So, we found actually in the peridoxin there are huge number of this NHS gamma interactions possible, and most of them actually observed in the tons. Okay. So, we are analyzing in detail how it is modulating those enzymatic activity, mostly the oxidation and reduction at the iron center. That is what we are looking at very closely. This is my last work. So, let us put everything here. So, I looked at, if you look at the definition of IPAC, it says XH, in which X is more electronegative than hydrogen. Okay. So, I thought of, can we have such interaction where the X could be more electropositive than hydrogen. Okay. And this is what we looked at manganese, iron, cobalt, and we found such interactions are possible. I submitted to some journal, and stating this was the title of the journal, and this was the reviewer comment. Okay. So, let me read it out. It was too hard actually, too discouraging. Of course, there are bonded interactions involving negatively polarized hydrogen atoms. It is a purely matter of taste and convention whether one calls them hydrogen bond. IPAC has decided not to call them hydrogen bond. Should not be published in any journal of RSC, even including the revision proposed by the authors. Okay. This was too discouraging. So, what we did, some other reviewer some other editor actually picked up the data when we submitted as a PCA, and it was appeared here in the Young Scientist issue. So, I am here. Okay. So, it was blessing in disguise to have the paper there. Okay. So, there are many challenges, and this is the challenges. What about the peridoxin stuff, the MHAO stuff, the SH radical stuff. These are the few challenges I spelled out here, and which can be verified with experiment. The principle of science, the definition almost is the following: the test of knowledge is experiment, experiment is the sole judge of scientific truth. Anyway, so I thank you all for your. These are my students, my mentors. So, because of them, I started the hydrogen bond looking at in different angle. So, this is our campus, and these are the photo we had taken before the super cyclone Fani. Okay. So, how the sky was looking like. So, they are so beautiful sky. Thank you all for your kind attention.
Thank you, Professor Biswal, for an excellent presentation. We have time for 2 questions.
In the metal hydrides, do you see any sigma hole behind hydrogen atoms?
Behind hydrogen atom?
Yeah, do you see any sigma holes?
Yeah, it's there a little bit.
Okay, I think that's probably.
No, but when I calculated the charges actually using the electrostatic
charges
potential,
won't tell you anything.
even if using the electrostatic potential,
doesn't matter. Charges won't tell you anything.
Could be, that could be reason, but it is possible. IPAC has to think.
Any other
Question?
If there are no further questions, let us thank Professor Biswal once again for this excellent presentation.